Hello dear students, welcome you all for Power System Operation and Control class. Continue with the module 4, that is voltage and reactive power control. In that today we are going to see the sensitivity of voltage to changes in real power and reactive power. So we are knowing that the voltage V at a node is a function of both real and reactive power, that is P and Q. So we can write V is a function of P and Q. So if we get the derivative of V, then we need to go for the derivation with respect to P as well as with respect to Q. That is dV is equal to dou V by dou P into dou dP plus dou V by dou Q into dQ. So if we go for a small adjustment or small correction here, that is what we are knowing, that dou P by dou V into dou V by dou P is the same one, because both the numerator and denominator get cancels. At the same time, dou Q by dou V into dou V by dou Q is equal to 1. This we are knowing. The same thing we will apply here, so that here dou V by dou P we are having no into dP. Then we are making the things such a way that dV can be given by, here dou V by dou P into dP is there, no, that dP by dou P by dou V is taken. Okay, because the things we are seeing here, then if you want the what is dou V, what is dou P, all those things we are known here, because you see in that previous equation, the dou P by dou V into dou V by dou P is there. Then if we want the dou V means we can get the dou P on other side, so we can have rearrange the equations. So here dou V by dou P is made here, and dou P by dou V taken into denominator. At the same time, dQ over dou Q by dou V is taken. Okay, then we are considering the figure 8.4, that is in the previous class we have seen one system is connected to a load with its impedance and all. I went to phasor diagrams I have shown there. So in that equation we are knowing that delta V is equal to E minus V, and from the equation 8.9 it is clear that E minus V into V minus RP minus XQ is equal to 0. That we are knowing in the 8.9 equation. Now here E is the sending end voltage and V is the receiving end voltage. So from the above equation we will write that dou P by dou V is equal to E minus 2V by R, and dou Q by dou V is equal to E minus 2V by X, or dV is equal to, these two things we will put in the equation, above equation. We can write dP by E minus 2V 1 by R plus dQ by E minus 2V by X. So we will consider this as the equation for dV. Next we will coming to the simplification of this one, taking the E minus 2V as the denominator. So dP of R in plus dQ X we will take there, or for constants V and delta V we have from the equation 8.18 dQ is equal to minus of R by X into dP. So this is regarding the, so from the equation 8.23 we see that the smaller the reactance associated with the node, the larger the value of dQ by dou Q by dou V, and hence from the equation 8.20 smaller the voltage drop. When more lines are incident on a node, the reactance will be smaller and hence voltage drop is lesser. So what is the implication of this one? That is that we will assume that one a node is system is having a drop of 2 kilovolt, and from the no load to full load, and the value of dou Q by dou V is at this node is 10 MVAr per kilovolt. Then to maintain the node voltage at its no load value, we need to inject, that is 10 into 2, that is 2 times 20 MVAr. This means if dou Q by dou V is higher, the more reactive power is needed to at the node to maintain the constant voltage. So when the system is on no load, V is equal to E, then equation from the equation 8.23, that is the magnitude of dou Q by dou V is same as E by X. E by X is nothing but the current when receiving end is short circuited and resistance is neglected. Therefore we can say that magnitude of dou Q by dou V is equal to short circuit current when V is equal to E. Under normal operating conditions, V is close to E, Hence, the equation 8.26 is useful as a thumb rule to know the reactive power requirement at the node. Since the short circuit current is normally known at the various buses. Okay, so this is regarding the sensitivity of the voltage changes in P and Q. We will see one problem here. 8.4, that is the three generating stations are connected to a common bus bar X as shown in the figure. For a particular system load, the line voltage at the bus bar falls by 2 kV. Calculate the reactive power injection required to bring back the voltage to original value. All values are on a 500 MVA base. So you can see the figure here. A point node we are having 275 kV. That is connected with a transformer at 0.1 per unit impedance, and J 50 ohms as reactance. X node is there. Then that node is connected with 50 ohms reactance to the node C. Another 50 ohms reactance plus one transformer with 0.1 per unit is connected to B, and each A, B is having 275 kV and C is having 132 kV. So solution is seen by the base of the impedance in 132 kV is nothing but kV square by MV. We are knowing that is 132 square by 500, we will get 34.848 ohms. Then ZL, the line reactance is given by 50 by 38, that is we are getting per unit value as 1.4348 per unit. The single phase equivalent circuit is like this. So the whatever the figure is there, that is if you converted it into single phase equivalent circuit, it is become as a 8.9. and then reactance from X to N is given by 1 over X equivalent, that is 1, we are knowing that 1 over X1 plus 1 over X2 plus 1 over X2, or we will get X equivalent as 0.5 per unit. So putting all the values here, we can do here. See, three reactances are there, that is in series we are adding, then it is in parallel. So 1 over J 0.15348 plus 1 over 1.5348 plus 1 over 1.4348. Then after adding all those things, you will get X equivalent as 0.5 per unit. Then short circuit current is nothing but E by X equivalent, that is 2 per unit. Base current is calculated using the power by voltage, that we will getting 2187 where the three phase. Then calculating that one, the base value with the per unit value, you will get the actual value of short circuit current, that is 4373 amps. When three phase reactive power is used, then V is line to line voltage, that's what dou Q by dou V is given by root 3 of ISC, which is nothing but 7574.2 watts per volt, or if you convert it into MVA, then MVA per kVA, so we can write 7.57 for MVA per kV. For a drop of 2 kilowatt, the reactive power need to be injected 2 times of that is 7.579 into 2, that is 15.148 MVAR to be injected. So this is what the solution of the problem. Okay, so next is the cost saving. Cost saving, we will consider one 2-point tariff, that is T is equal to X kVA plus Y kW rupees. We are seeing it in the previous our generation and all 2-part tariff. So X changes with for the kV and Y for the kilowatt hour. So let us draw the active power P1 at the power factor cos phi 1, or kVA is P1 by cos phi 1. If the power factor improved to cos phi 2, then kVA is P1 by cos phi 2. The saving in cost is X into P1 by cos phi 1 minus P1 by cos phi 2. The reactive power required to change the power factor is P10 phi 1 minus P10 phi 2 kVAR. If the cost of the installation is rupees C per kVAR, then total cost of installation is CP1 into 10 phi 1 minus 10 phi 2. Hence the net saving is given by saving is equal to X into P1 into 1 over cos phi 1 minus 1 over cos phi 2 minus C into P1 10 phi 1 minus 10 phi 2 rupees. So maximum saving can be obtained, that D saving by D phi 2, the differentiating the saving with respect to the phi 2 angle, then when equating it to 0, we will get sin phi 2 is equal to C by X. From this equation, we observe that the optimum power factor does not depend on the initial power factor. Further, optimum power factor is not unity from the cost perspective. So this is regarding the cost saving. So in the next class, we are going to see the methods of voltage control by reactive power injection. So for the time being, we will stop the class here. Thank you.